everyone, welcome to Learning at 11th Hour. In this video, I'm going to show you how we can design a 3-bit binary to gray code converter. Before we begin, let me tell you a little bit about the gray code. So, when there are two consecutive numbers in the gray code, if we observe it very closely, there will be only one bit that changes between the two consecutive numbers. For example, if you look at the numbers in this binary representation, so this number is 1, whereas this one is 2 in decimal, right? So, looking at this binary representation, to change from 1 to 2, we need to change 2 bits. B naught will become 1 to 0, B1 becomes 0 to 1. So, 2 bits are changing at the same time. Whereas in case of gray code, that is not allowed. Only one bit will be changing between two consecutive numbers, which is why the gray code is also called as unit distance code, because the distance between two consecutive codes is just one bit. Now, in order to uh, design any logic circuit for that matter, we need to know the truth table first. So, I'm going to help you develop the truth table for this particular design. In order to find out the gray code representation of any binary number, we need to retain the MSB as it is. So the binary MSB will be retained as the gray code MSB. So that is the first step. So let me write it out: 0, 0, 0, 0, 1, 1, 1, 1. Now, in order to find out G1, we need to add B2 with B1 and discard the carry. So G1 is nothing but B2 plus B1 with the carry discarded, if there is any that's generated, right? So let me fill that up. So in this case, we have uh, G1 is 0 plus 0, 0. G1 in this case is 0 plus 0, again 0. 0 plus 1 is 1. 0 plus 1 is 1. So this is basically binary addition. That's one thing we need to keep in mind. 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 0, we discard the carry. Again, 1 plus 1 is 0, we discard the carry. In order to find out G naught, we need to add B1 with B naught and again discard the carry. So here we are going to add 0 plus 0, B1 and B naught. So this is going to be 0. 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1, 0, discard the carry. This is 0, 1, 1, 0. So now that our truth table is ready, the next step is to obtain the K maps for each of these bits, G2, G1 and G0. So the K map for G2, it can be obtained using a grid with just 3 variables involved. So a 3 variable K map, in this case, we have B2, B1, B0 as our inputs. 0 0 0 1 1 1 1 0 0 and 1. So I'll write out the minterm numbers so that it's easy for us. Now here for G2 we have 4, 5, 6 and 7 as our minterms. So basically G2 is equal to 4, 5, 6 and 7. So this is where we mark our ones. If we see, this in itself is forming a quad, and the expression for this is going to be B2, which is pretty obvious because the MSB of the binary and the MSB of the gray, we had kept it the same. Now we're going to find out the K map for G1. So in case of G1, if we see, G1 is equal to 2, 3, 4, and 5. So 2, 3, 4, 5. So these are the minterms involved. So let me draw the K map to obtain the expression now. So here we have B2, B1, B0, and so this is, let me fill it up as 2, 3, 4, and 5. So we can have two pairs. This is nothing but B2 dash, and if you look at the columns, we have B1 common here, and the expression for this group is B2, and here we have B1 dash common when we analyze the columns. So we can write out G1 as B2 dash B1 plus B2 B1 dash, which is nothing but B1 XORed with B2. Now let's find out the expression for G0. The minterms are 1, 2, 5, and 6. So let me write it out. The K map for G0, 1, 2, 5, and 6. So here we have again the three variable K map, B2, B1, B0 being the inputs, and these are the minterm numbers. Now let me mark the minterms in the K map, 1, 2, 5, and 6. So again we have two pairs, this one and this one. The expression for this being B1 B0 dash, and the expression for this being B1 dash B0. Therefore we can say that G0 is B1 dash B0 plus B1 B0 dash, which is nothing but the XOR of B1 and B0. So enlisting all the expressions that we've got, we can now develop the logic diagram. So G2 is B2, G1 is B2 XOR B1, G0 is B1 XOR B0. So my inputs are going to be this is B2, B1, B0. So B2 is going to be equal to G2, but B2 XORed with B1 is G1, and B1 XORed with B0 is G0. So this is the logic diagram for my binary to gray code converter for 3 bits. In case we want to design this for 4 bits, we'll have to include another bit B3, and all the expressions will change because now B3 would become the MSB. But what holds good is that uh, these terms remain the same, right? So G1 will still be B2 plus B1, G0 is B1 plus B0, G2 will be B3 plus B2 in that case. So you could try that out, and even in that case, you should get a similar structure for implementing the binary to gray code converter. So that's all with this video. I hope the binary to gray code conversion is clear to you all. Thanks for watching.